Think about every single email you read this morning, all the articles you skimmed through, or the text messages you just fired off. Now, what if I told you that a massive portion of every single letter in those messages is, strictly speaking, completely unnecessary? I mean, your brain is actually doing an incredible amount of heavy lifting right now, just filtering out letters that don't actually convey any new information at all.
Get ready for this, because statistically speaking, up to 75% of the English language is entirely redundant. Think about that. That means if we were being purely efficient about it, we could potentially slash 3/4 of the letters right out of our alphabet and still communicate the exact same meaning. It sounds totally impossible, right? Like some wild exaggeration? But it isn't a guess. It's actually mathematically proven.
Welcome to this explainer. Today, we're unpacking a seriously mind-bending paper from 1951 by the founding father of information theory, Claude Shannon. In Prediction and Entropy of Printed English, he set out to mathematically measure the raw, unadulterated information that's actually contained inside our language.
All right, let's just dive right into this. To really grasp Shannon's work, we first have to understand the core concept he was trying to measure, which is entropy. In information theory, entropy is essentially the statistical parameter that measures how much actual information is produced, on average, for each letter of a text. You can basically think of entropy as the element of surprise. If a letter is totally unpredictable, well, it gives you maximum information, meaning it has high entropy. But if you already knew what the letter was going to be before you even looked at it, it gives you zero information.
And that brings us to the exact opposite of entropy, redundancy. Redundancy measures the constraints that are forced onto a text by the underlying statistical structure of the language itself. Take the letters Q and U, for example. If I give you a Q in an English word, you know with near absolute certainty that the very next letter is going to be U. Because of that massive structural constraint, that U is highly predictable. It carries incredibly low entropy. The English language is absolutely packed with these invisible rules. We're not just talking about pairs of letters, but frequencies of words, strict grammar rules, and all those common idioms we use every day.
So Shannon initially tried to tackle this using dense mathematical formulas, calculating what's known as n-gram entropy. Basically, this meant calculating the probabilities of specific blocks of letters following other blocks. If you have an alphabet of 26 letters plus a space, calculating the exact statistical probability of single letters, then pairs of letters, then triplets, well, it gets exponentially complex. By the time you try to map out the statistics of 8-letter sequences, the math becomes overwhelmingly complicated. And obviously, language extends way beyond just 8-letter patterns. It stretches across whole phrases and entirely long paragraphs.
Shannon realized that purely mathematical formulas were hitting a brick wall. He needed a way to account for those long-range statistics, the kind that span across entire sentences. And this is the crucial pivot. Shannon realized he already had access to the perfect supercomputer to calculate these probabilities: the human brain. He deduced that anyone speaking a language already possesses, intuitively, an enormous implicit knowledge of the statistics of that language. Our everyday familiarity with words, idioms, and grammar allows us to just effortlessly fill in the blanks. Basically, human intuition became his scientific instrument.
Let's actually test this right now with a real example straight from Shannon's experiments. Just imagine you're presented with a phrase that starts, "The room was not very light. A small oblong." Mentally put yourself in the shoes of his test subjects for a second. If you see the letters T and H, your brain instantly predicts an E, or, maybe an A. When the preceding text is already known, the next letter becomes wildly predictable.
Shannon set up this guessing game with some very specific, simple rules. The subject guesses the next letter. If they get it right, they're told so, and the letter is recorded simply as a dash. Then they move right along to guess the next letter. If they guess wrong, they write down the correct letter and try again for the next one. What this produced was absolutely fascinating. It created what Shannon called a reduced text, a sequence made up almost entirely of dashes, peppered only with the letters where the human subject actually guessed incorrectly. It was, in essence, a text of pure unpredictability.
And this perfectly illustrates his next big leap. Shannon proposed a theoretical communication system, essentially a predictor circuit, using this newly created reduced text. He argued that the original sentence, completely full of words, and the reduced text, full of dashes and mistakes, actually contain the exact same amount of information. To prove it, he proposed an identical twin thought experiment. Picture placing the person who did the original guessing on one side, and their exact identical twin on the other side of a communication line.
Let's break down how this builds into a perfect reconstruction loop. Step 1. You only send the reduced text, so just the dashes and the mistakes, over a wire to the twin. Step 2. The twin, acting as a perfect reversible transducer, looks at a dash and makes their own guess. Because they are mathematically identical to the first person, they are going to make the exact same correct guess the first twin did. If they see a letter, they know they would have guessed wrong, so they just accept the provided letter and move on. Step 3. By just transmitting the mistakes, the twin flawlessly rebuilds the entire original message. It proves, without a doubt, that the predictable letters carry zero necessary information to transmit the message.
But Shannon kept pushing the boundaries. In a reverse guessing experiment, using the phrase, "there is no reverse on a motorcycle," subjects guessed the correct letter on the very first try, a staggering 79 times out of 102 symbols. That is 79 instances where the letter provided absolutely no new information to the reader simply because their brain already knew what it was going to be before it even appeared. Now, of course, the level of predictability really depends on what you're reading. Shannon Riley noted in his paper that newspaper writing, scientific work, and poetry generally lead to somewhat poorer scores. Ordinary literary English, highly predictable. But when a poet starts bending the rules of language, or a journalist packs dense, completely unexpected facts into a sentence, entropy spikes. The text becomes less predictable, which mathematically means it is carrying way more information per letter.
What's really incredible about his process is how Shannon took all of this intuitive human data and brought it straight back into the realm of hard mathematics. He used his human data to establish mathematical inequalities through a process called rectangular decomposition. Essentially, he proved that an ideal predictor, a theoretical perfect machine, would have an entropy score lower than or equal to his human subjects. He literally turned human intuition into definitive upper and lower mathematical bounds.
Which leads us to the grand culmination of his data. Watch what happens as the subject learns more of the sentence, moving from knowing just one preceding letter to 5, all the way up to 15. The upper and lower mathematical bounds actually swoop downwards and begin to beautifully stabilize and converge.
So, what is the final verdict of those converging lines? Shannon concluded that when you take into account the long-range statistical effects, the context extending up to 100 letters, spanning across entire phrases and paragraphs, the entropy of ordinary literary English reduces to roughly 1 single bit per letter. Since a totally random 27-symbol alphabet could carry 4.7 bits per letter, operating at just 1 bit means our language is roughly 75% redundant. Literally 3/4 of the letters we use are just structural scaffolding. Which leaves us with a truly profound thought to walk away with today. Our brains are incredibly efficient prediction machines, seamlessly gliding over the rigid constraints of language, entirely ignoring the 75% of text that is mathematically just filler. But if 3/4 of every sentence you speak, type, or read is totally predictable, it really makes you wonder, what true, unpredictable value are you injecting into the world with that remaining 25%?